Good morning, everyone. So welcome to my YouTube channel, Maths of Karam. So today we are going to see 13th lecture on functions of bounded variation. Till now, if you have not subscribed my YouTube channel, subscribe it immediately for such type of interesting topics. Okay. So let's start today's lecture now. We recall the theorem of 11th lecture on functions of bounded variation. What was that theorem? Let f be a function of bounded variation from closed interval ab to r. Then there exist unique monotonically increasing functions p and q from closed interval ab to r such that f is p minus q and the variation function of f is equal to p plus q. Okay, so we have studied this theorem in lecture number 11 on functions of bounded variation. You can find a playlist on it and you can see the 11th lecture. You can understand this from that lecture. Okay. So I am recalling it because I need in this lecture. Okay. So actually, this P is called positive part of F. P is called positive part of F. And Q is called negative part of F. Okay. So what I am saying that P is called positive part of F and Q is called negative part of F. Okay. So, but in actual, this is P is just a positive part, but being a positive part is just a name of P. Okay. In actual, P need not be a positive function. Okay. Similarly, Q is just a name. Q is a negative part. Negative part is just a name. In actual, Q need not be a negative function. You can see the example. So observation 1. So first of all, P is nothing but 1 by 2 Pf plus F. And Q is 1 by 2 Bf minus F. You can see the proof of in lecture number 11. You will find that first thing I have written in that lecture. Okay. Now, you observe one thing. P is although positive part of F, but this is just a name. In actual, P need not be a positive function. See the example. I am taking fx is equal to x on closed interval minus 1 to 1, minus 2 to 1. Okay. Because this is a monotonically increasing function. So obviously it is function of bounded variation. Now, okay. Now you see that P evaluated at minus 2. So 1 by 2 Bf at minus 2 plus F evaluated at minus 2. But we know that variation function at initial point is 0. So I have put on the value. I put the value 0 in place of Bf minus 2. And F at minus 2 is nothing but minus 2. F put the value. So this is minus 2 upon 2, that is minus 1. But minus 1 is negative. Okay. Although the P has name positive part of F, but in actual it is giving negative value. So saying that P is a positive part does not imply that P is a positive function. Okay. So P need not be a positive function. Now observe that Q although negative part of F, but this is just a name. In actual, Q need not be a negative function. See the example. Same example I am taking. Fx is equal to x on closed interval minus 2 to minus 1. Okay. Q is equal to 1 by 2 Bf minus F. So you evaluate Q at minus 2. So you will get Q at minus 2 is equal to 1 by 2 Bf at minus 2 minus f minus 2. Again, the variation function at the initial point is always a zero function, has a zero value. So I have put the value 0. And what is f at minus 2? It is minus 2. So there is a minus sign, so it will be positive 2. So 2 upon 2 is 1. Although, so we have value 1 of q at minus 2, that is positive. Although q has name negative part of f, but actually it is giving the value positive at minus 2. It means q need not be a positive function. Okay. Now I am doing a question. Let f be a function of bounded variation on closed interval AB, and p and q are positive and negative part of f respectively. Then p and q are of minimum variation in the sense that so then p and q are of minimum variation in the sense that if there exists p1 and q1 from closed interval AB to R monotonically increasing function such that the difference of f is difference of base function, then the variation of p is less than variation of p1 and variation of q is less than equal to variation of q1. Okay. So such things happen because positive and negative parts also have their difference. P minus q is equal to f. Okay. If you have another function p1 and q1 monotonically increasing and f is nothing but p1 minus q1, then the variation of p1 p is less than equal to variation of p1 and variation of q less than equal to variation of q1. Okay. So let's start its solution. So I know that p is 1 by 2 bf plus f and q is 1 by 2 bf minus f. So I can write 2, I can take 2 here. 2p is equal to bf plus f will be there. Okay. Now, what is 2px? This is nothing but bfx plus f. It means 2px is equal to bf ax. What is f? p1 minus q1. So this implies 2px is equal to bfax plus p1x minus q1x. Okay. So what is 2pb? It is pb plus p1b minus q1b. So this implies 2pb is equal to, what is this? This is variation of f plus p1b minus q1b. Okay. And what is 2pa? 2PA is equal to okay. What is this? This is 0 because this is value of BF in base evaluated at A. That is, this is 0 plus P1A minus Q1A. Okay. So this is equal to, this implies 2PA is equal to P1A minus Q1A. Let's say it's equation number 1. Okay. And let's say it's equation number 2. Okay. So from 1 and 2, we have what we have 2 times PB minus 2 times, what is this, BF plus P1B minus Q1B minus P1A minus Q1A. Okay. What is this? So I can write it P1B minus P1A minus Q1B minus Q1A. So what is this? What is this? BF. P1 is a monotonically increasing function. When you have a monotonically increasing function, so what is this? This is variation of P1. Or what is this? This is variation of Q1. Okay. Since P1 and Q1 are monotonically increasing functions. So what is the variation of P1? P1B minus P1A. Okay. And what is the variation of Q1? Q1B minus Q1A. Okay. Q1A. So we have this one. Okay. So this implies, and so what is this? So this implies, I can take 2 common. This is BF plus BP1 minus VQ1. Okay. So here P is also, so P is also because since P1, Q1 and P, because P is also monotonically increasing now. So what is the variation of P? BP is equal to PB minus PA. Okay. PB minus PA. So put this value there. This is equal to 2BP and this is equal to okay. But F is equal to P1 minus Q1. So F is equal to what is F? F is P1 minus Q1 plus BP1 BQ1 because F is equal to P1 minus Q1. So this implies 2BP is equal to okay. So this implies, but we have this one, this inequality. The variation of P1 minus P1 minus Q1 is less than variation of BP1 plus VQ1. Okay. Because variation of BP1 minus Q1 is less than equal to variation of BP1 plus variation of VQ1. Okay. So this implies 2BP. So this will be cancelled out. Is less than equal to 2 times. Okay. So this is cancelled out. So this implies BP is less than equal to BP1. So one is proved. Okay. Next, what is this? What is QX? What is Q is 1 by 2 upon BF minus F. Okay. So what is so I can write this. This implies 2Q is equal to 2Q is equal to BF minus F. So what is 2QX is equal to BFX minus FF. So what is this? 2QX is equal to BFAX, okay, minus FF. This implies 2B is equal to BFAB minus FB. Okay, just write the function. What is F? F is nothing but P1 minus Q1. Okay. So this implies 2qx is equal to bf ax minus p1x minus q1x. Okay. Because nothing but t1 minus t. So this implies 2qx is equal to bf ax minus p1x plus q1x. So what is 2qb? Okay. So this is nothing but variation of f. Let's say equation number 3. And what is 2qa? bf aa minus p1a plus q1a. But this is 0. Okay. p2a is equal to minus p1a plus q1a. From 3 and 4, we have we have 2qb minus 2qa. bf minus p1b plus q1b plus p1b minus q1a. So this is a here. Okay. Okay. So taking 2 common from here, so I can write it minus p1b minus p1a plus q1b minus q1a. But q p p1 q1 and q are monotonically increasing. Since p1 q1 and q are monotonically increasing functions, so they are functions of bounded variation, and their variation is given by bp1 is equal to p1b minus p1a. I already told this for p1. bq1 is equal to q1b minus q1a. Okay. And what is VQ QB minus QE. Put these values here. Okay. So put these values here. So what is this? 2 times, this is variation of Q. This is BF. This is variation of F. This is variation of P1. And this is variation of P1. But the variation, but what is F? P1 minus Q1. Okay. But this is less than BP1 plus BQ1. So it will remain as it is. Other things will remain. Because BP1 minus Q1 is less than BP1 plus VQ1. Okay. This is Q1. So this is cancel out. So this implies 2VQ, which is less than equal to 2 times VQ1. This is cancel out. So this implies VQ is less than equal to hence BP is less than BP1 and VQ is less than VQ. We are done. Okay. So we have done this question. Okay. So now we are doing one corollary. I am writing one corollary. Let F from closed interval AB to R be a function of bounded variation. Then BP is nothing but minimum of P of VQ1 such that P1 Q1 from following interval AB to R monotonically increasing and F is P1 minus Q1. Okay. And VQ is equal to minimum of this is minimum of BP1. And this is minimum of BQ1, P1, Q1 from closed interval AB to R monotonically increasing, and F is equal to P1 minus Q1. Okay, let's prove it. Let P1 Q1 from closed interval AB to R be monotonically increasing. Monotonically increasing functions. Okay, function such that F is equal to P1 minus Q. By question, just above question, we have done the question above. By that question, we have BP is less than equal to BP1 and okay, and VQ is less than VQ1. Okay. So from this, what we have? We have BP is less than equal to minimum of infimum of BP1 such that P1 Q1 from closed interval AB to R monotonically increasing such that F is equal to P1 minus Q. And from here, what is this clear? From here, if I am taking this, what I will get? So I am writing here VQ is equal to infimum of VQ1 such that P1 Q1 from closed interval AB to R monotonically increasing such that F is equal to P1 minus Q1. Okay. Okay. Let's say it's equation number 5 and let's say it's equation number 6. Okay. But F is also P minus Q. Therefore, infimum mums in 5 and 6 will exist and will be equal to BP, BQ respectively. Because infimum's lower bound is nothing but lower bound. I'm taking infimum. Infimum is greater than equal to BP. But BP is also member of this family. Okay. So it means infimum will exist and that will be minimum of this family. Similarly, VQ is less than equal to infimum of this. But Q is also member of this family as F is equal to P minus Q. So infimum will exist and that will be minimum of this family and that is equal to VQ. Okay. Therefore, hence we conclude BP is equal to minimum of BP1 such that P1 and Q1 from closed interval AB to R monotonically increasing such that F is equal to P1 minus Q1. Okay. And VQ is equal to minimum of VQ1. Okay. Such that P1, Q1 from closed interval AB to R. Okay. Monotonically increasing such that F is equal to P1. Okay. So it is done. Okay. So today's lecture up to this. If you have any problem related to this lecture, you can comment me on my YouTube channel. So like, share, comment, and subscribe my YouTube channel. Thank you very much for today's lecture. Thank you very much. We will see you in next lecture.